Good afternoon, students. Let us start the first HDL lab class. On the screen, you are seeing a comparison table for Vhdl versus Verilog. This is a brief introduction about how we are going to use these two programming languages. I'll not go into too much of detail, but some of the points which you have to remember when we conduct lab classes. For that purpose, I'm discussing this particular table. Vhdl is case insensitive and Verilog is case sensitive. An easy way for you to remember this is, see, Vhdl contains all capital letters, where Verilog contains one capital letter and others are all small letters. So in the word Verilog itself, both cases are there. So you can remember that it is case sensitive. Whereas Vhdl, all caps are there, which means it is case insensitive. In the sense, any identifier or name of input or output port, or even the module name, entity name, architecture name, in Vhdl it is case insensitive. It can be a combination of capital as well as small letters. But in Verilog, if you type a combination of small and capital letters, separately capital letters, separately small letters, they're all taken as different identifiers. Now in Vhdl there are many data types, whereas in Verilog there are limited data types. This anyhow we are going to see in the theory class. Vhdl is based on the programming language Pascal and Verilog is based on the programming language C. So in the case of Verilog, typing work is lesser, whereas in the case of Vhdl, typing work is more. And in the case of Vhdl, library files can be included. Always we type library IEEE and then we use some packages. In Vhdl, we have many packages, out of which whichever package is useful for our given experiment or given project, we can include it in our program. Whereas in Verilog, there is no such library management because it's a single library which need not be mentioned when we execute the program. And that single library contains all the data that is required for execution of the programs or projects. Vhdl was standardized by IEEE in 1987 and Verilog was standardized by IEEE in 1995. And in Vhdl, large structures are possible, whereas Verilog cannot handle really very large designs. For example, Verilog is easy to write, easy to work with. So generally industrial people who develop consumer products, they use Verilog for their designs. Whereas the larger scientific applications or maybe the multidisciplinary technical or engineering applications, when people design such products, they prefer Vhdl. For example, in Bengaluru, ISRO and DRDO and all other defense establishments, even now they use Vhdl only for their designs. The reason is Vhdl is a very vast language and it is possible to have much larger designs because of the usage of packages. Whereas Verilog is easy to handle, but when there are complicated designs such as real-time systems, now Verilog will introduce some issues there which may not be so easy to solve as such. So that is how both the languages are under usage. Vhdl is also under usage, Verilog is also under usage. Vhdl is like Pascal, more of typing work, but it is well structured, whereas Verilog, as far as typing is concerned, is lesser, but it is not so well structured compared to Vhdl. So if there are bugs in a bigger project using Verilog, it will take a much longer time to resolve the bug or resolve the error. Whereas in Vhdl, it is somewhat easier to correct the errors. So editing style wise, Vhdl is more verbose and Verilog is concise, as I have already told. Now this is the program style. You can see the program style. In Vhdl, there is a separate entity declaration, separate architecture declaration. Inside the entity, we will declare the I/O ports. Inside the architecture, we will describe the relations between the ports. Whereas in the case of Verilog, it is simply module and end module. In between module and end module, in the beginning we will declare the I/O ports. Later on, we will start with the declaration of relationship between these ports. So there is no demarcation which is present in Vhdl. In Vhdl, ports are declared first, then they are related. In Verilog, everything happens inside the module itself. So in Vhdl, semicolon is not put at the beginning of the entity and architecture, it is inserted at the end of both of them. Whereas in Verilog, semicolon is inserted at the beginning of the module, it is not put while ending the module. You can see there, entity circuit is, there is no semicolon, but when you end it, there is a semicolon. Architecture C1 of circuit is, there is no semicolon, when you end it, there is semicolon. Whereas in Verilog module circuit, in the beginning there is semicolon, at the end there is no semicolon. These are two different styles. Just like we have European styles and American styles. Europeans have right hand drive, Americans have left hand drive. Europeans use 220 volts, Americans use 110 volts. Americans have purposefully developed their own style to be different from the European style. It is that way here also. Vhdl has one style, Verilog has one style. Now, in case of Vhdl, we declare the variables or the signals in this way. A in standard underscore logic, B out standard underscore logic. A is the input signal, B is the output signal. And we use a package called standard underscore logic. Whereas in in Verilog, we directly put input A semicolon, output B semicolon. This is how we declare it. Now, if it is a vector, vector means it is having more than one bit. Don't get confused with the vector which we use in mathematics. In HDL, vector means any input or output signal that is containing more than one bit. So here in Vhdl, A in standard logic vector 3 down to 0 means it is 4 bits. Similarly, B out standard logic vector 7 down to 0 means it is 8 bits. Similarly, in Verilog, we can define it as input, and within brackets we will put 3 is to 0, then we declare it as A. Output within brackets we will declare it as 7 is to 0 and declare it as B. So here parentheses are used in Vhdl, whereas in Verilog brackets are used. Now Vhdl can have 9 logic values: 0, 1, X, L, H, W, Z, U and hyphen. So these hyphen is don't care. 0 and 1 are already there. X is unknown. Z is high impedance. L means weak 0. H means weak 1. And U means weak, W means weak unknown. You have already told it is unknown. So in this way, when we use this standard underscore logic, Vhdl can have 9 logic values. Whereas in Verilog, there are only 4 logic values called 0, 1, X and Z. X means unknown. X can be 0, X can be 1, but right now it is unknown. For example, whenever we have this shifting of the vector, now when we move from right to left, one more bit has to be added at the right side. It will become by default X, because it may be 0, it may be 1. Right now it is unknown. Z means it is neither 0 nor 1. In general, 0 means current is sinking to the ground. 1 means current is sourcing into the output from the power supply. You will have to visualize the Cmos inverter here. When current is sourcing through P MOSFET, then that is 1. When current is sinking through N MOSFET, that is 0. Simultaneously, both of them cannot be on. But if the input is in the middle of the power supply, let us say the input is at VDD by 2, then partly both MOSFETs will be on. Partly when both MOSFETs are on, both will work like a very high resistance, and even the output will be at VDD by 2. There it will neither be sourcing nor be sinking, then it is called as high impedance. So in Verilog we have 0, 1, X and Z, only 4 values, whereas Vhdl is vast. Here 0 means 0 volts, 1 means VDD, X means unknown as I told. Now L can be in between 0 and VDD by 2. That is taken as weak low, weak 0. Similarly, if that particular logic value is between VDD by 2 and VDD, then it is called as weak 1. Similarly, if this unknown itself is weak, then it is called W. Z, I have already told you, high impedance. It is VDD by 2 only. And U, I have told you, it is unknown. Here hyphen means don't care. In that way, VHDL has a larger options of logic values. Now, coming to sequential execution and concurrent execution, I should tell you a little of what is meant by concurrency and what is meant by sequentiality. HDL as such is concurrent. Hardware description language as such is concurrent compared to all other programming languages. And I keep on giving the example of Ravana for this. Ravana has 10 heads, and if you give 10 plate meals, he can consume all the 10 plate meals at once. Whereas Kumbhakarna can also eat 10 plate meals, but only one after the other. So that way we can say Ravana is corresponding to concurrency and Kumbhakarna is corresponding to sequentiality. Now, why HDL has to be concurrent by default? The reason is all combinational logic circuits are basically concurrent. In the sense, if you have a full adder, for the full adder you are going to give 2 input bits and the carry input, and the full adder is going to compute sum and carry output. Now, as soon as the input value changes, immediately output value changes, except for the propagation delay of the gates. It is concurrent, or it is simultaneous, or it is parallel execution, we can say. That means A, B, C in is going to be immediately computed at sum and carry out, and whenever the value of A, B or carry in changes, the sum or carry out values also instantaneously change. And that is called concurrent logic. And we are not going to give A separately, B separately, C in separately. So all the combinational circuits are basically having a concurrent execution. That is why HDL is designed as a concurrent execution. More about it I am going to tell you later on when we start executing such programs. Okay, now all sequential circuits are by default, their name itself says they are sequential. In the sense, in the case of a JK flip-flop, even if J changes or K changes, output will not change until the clock's edge changes, right? If it is a rising edge triggered clock, when clock goes from 0 to 1, then only output Q and Q bar change. Otherwise, even when J and K values change, it will not change. That means it is following a sequence. It is one after the other. All the flip-flops, counters, registers, and every clock-enabled circuit is basically a sequential circuit, which means for computing the output, we have to wait for a particular event to occur. That is called sequential execution. So HDL as such is concurrent. HDL is meant for writing the code for combinational circuit directly. Whenever we want HDL to have a sequential design, we have to make the concurrent or combinational type into sequential type, which means we have to tell Ravana that we don't have 10 plate meals at once right now. We will give one plate after the other. Otherwise, Ravana is capable of consuming 10 plates at once. But in sequentiality, we have to follow one event, after that one more event, after that one more event. So we are telling Ravana, from now on, you are going to consume one plate at once. Now to give you one more real life example, because this is important, you will have to understand what is concurrency, what is sequentiality. So if you have to give one more real life example, let us say when you come to college, let us say 4 of you as friends will keep walking together in the corridor. Imagine that way. All 4 of you are walking together in the corridor. Now let us say I come from the back side. If I come from the back side, to give way for me, at least you will respect your professor, right? To give way for me, all 4 of you will break your parallel walking and you will go one behind the other. That means now you follow a sequence of walking one after the other. Now when you all walk together, that is concurrency. When you walk one after the other, that is sequentiality. I hope you understood this now. In the same way, HDL is basically a language which is concurrent. Means all the inputs if you give, if you don't tell the language that there is a sequence that is going to happen, by default, the language is concurrent. Whatever code you write, it is going to be concurrently executed. In the sense, between your architecture's begin and end, or between your model's beginning and end, whatever statements you give, all the statements will be parallelly executed. Because you are not told the sequence. It is like Ravana. As I told you, all combinational circuits are basically concurrent, and that is how the language is designed. Now, if you want to design a flip-flop or a counter or any other sequential circuit, such as memory, then you are going to tell or you are going to specify where exactly the sequential execution is going to start. For that, we have such keywords. That's why you can see here this keyword called process. This keyword called process. This indicates that it is the sequential execution that is starting. Otherwise, HDL will not know that it is sequentiality. Similarly, in Verilog, we have this keyword called always. Always at A comma B, where whatever is happening inside this begin and end, that is dependent on this A and B. Whenever A and B change, automatically inside the execution changes or the value changes. So this A comma B, which is given inside the parenthesis, is called sensitivity list. Here also A comma B given inside the process is called sensitivity list. Means the execution is sensitive to these particular variables. So VHDL uses a keyword called process and Verilog uses a keyword called always, and these are the two keywords which are used to tell Ravana that from now on it is sequential execution. Until then it is concurrent execution. Okay. So I hope you have understood what is the difference between sequentiality and concurrency. And let me stop annotating now. I should tell my colleague Richard to mute. Richard, can you mute yourself? Okay, let me continue. If students have any questions, you can ask me now. If at all you have any doubts regarding concurrence and sequentiality. Any questions here till now?
So why isn't there a semicolon after always, sir?
Okay, here semicolon will come as a delimiter. After always, we are starting one block called always. Inside this begin and end, we will have another execution statements. We will have many statements which are going to be assignment statements or executing statements. So semicolon will come only when there is a delimiter. It is separating between one statement to another statement. Here this is not an always statement, it is an always block. Okay. But as I told you, Verilog will not use semicolon at the end. So you can see that there is no semicolon here after the end. Whereas Vhdl uses semicolon at the end. That's why you can see end process, there's a semicolon here. That is the difference between Verilog and Vhdl. It is a style there. Otherwise, semicolon will be used as a delimiter inside the codes. That I am going to show you when we start working out with the examples. Any other questions? Okay, let me continue. You can also see this here, assignment. What is meant by assignment? We are technical people, and whenever we use a particular word, the word will have different meanings as per the context. So here assignment means whatever is computed at the right side is going to be assigned to the left side. You can see in this Vhdl statement, A and B means it is the logical AND operation between A and B, and it is assigned, the value of the output is assigned to the another signal called C. Now A and B are the two input ports, C is the output port. So the value of the computation of the right side is going to be assigned to the left side. That is why this particular symbol, you should not tell it as a less than or equal to symbol. We should keep on telling it as an assignment operator. Now this whole thing is an assignment operator. It is a less than or equal to symbol only when we use it in mathematics. But in the software language, when we use it, this is an assignment operator. Similarly, in Verilog, you have to specifically say the word assign and you have to use this symbol equals. Now in Verilog, this is the assignment operator. This equal symbol is the assignment operator. And why do we put this keyword assign? And why have we not put keyword assign here in Vhdl? Is a different reason now. In Verilog, whenever you have a concurrent assignment, you have to specifically say the word assign. But in Vhdl, that is not required because the Vhdl style is something different. When we involve more into the programs, one by one, you will try to understand these things. For today's class, it will be too heavy for you if I discuss all those things. I'll give an example here. In Vhdl, entity is separate and architecture is separate, and there can be multiple architectures. Each architecture is capable of understanding the assignment statements on its own. Whereas in Verilog, we don't have entity and architecture. We have only module and end module. In between them, we can have a concurrent execution, we can have a sequential execution. So whenever we have a concurrent execution, we have to specifically say assign. Whenever we have a sequential execution, we do not say assign. That is when we tell the tool, the software tool, that this is sequential execution, and if at all we specifically say assign, then that is a concurrent execution. Let me discuss this again. See now, in Verilog, both of these statements are going to be executed together. I gave an example of 4 people walking in a corridor. In the same way, even though these statements are written one after the other, writing of the statements can be one after the other, but execution happens together. That's why I gave the example of Ravana. Now, there will not be any delay for computing C and D. C and D will be computed together. One is AND gate and one is NOR gate. Right, upper one is AND gate here, lower one is NOR gate. both C and D outputs will be available together parallelly. Let there be 1,000 statements like this, one after the other. All the 1,000 statements will be executed parallelly, concurrently. That is the power of HDL. Why? Because all the combinational logic circuits are concurrent. Let us say any combination logic circuit is containing 1,000 inputs and let us say 100 outputs. All the 100 outputs will be computed parallelly when any of these 1,000 inputs are going to change. That is called concurrency. So, in Verilog, when we say that it is a concurrent execution, we use this keyword assign. In VHDL, we do not use it as such because VHDL is different style, Verilog is different style. Later on, even in the theory classes, we are going to discuss about this in larger detail. In Verilog, we have again blocking assignment and a non-blocking assignment inside the sequential assignment. When it comes to those topics, in the theory class, it will be discussed in detail. So let me proceed now. Now the assignment sequential, when 0, 0, assign D out to 0, 0, 0, 1. This is like a case statement. When the input is 0, 0, output should be assigned with 0, 0, 0, 1. This is the style in VHDL. Whereas in Verilog, the style is 2 and apostrophe B00 colon D out equals 4 apostrophe B0001 semicolon. Purpose is the same in both of them. Only thing is the style is different. You can see here, when input is 0, 0, let us say A and B are 0, 0, D out is assigned with the value 0, 0, 0, 1. Whereas in Verilog, we say input is 0, 0, 2 positions binary. This B stands for binary and 2 is 2 positions. So the output D out is assigned with again 4 positions binary 0, 0, 0, 1. And in VHDL, we are using this double quote for vectors. Whereas in Verilog, we are using this 2 apostrophe B or 4 apostrophe B. This is the style. Now the assignment symbols in VHDL, signal assignment is like this, variable assignment is like this. Signal means the one which is declared inside the entity block. Variable means the one which is declared inside the architecture block. You have already studied C language. So you already are familiar with the local variables and global variables. Similarly here, signal means it is like global variables. Variable itself means like it is local variables. That is why we generally do not use the word variable in general here, because in HDL or in VHDL specifically, the word variable itself is having a different meaning. Variable means it can be declared temporarily for some temporary execution inside one particular architecture. It cannot be utilized by the other architectures. That is why the symbol is different here for variable assignment. But for signal assignment, when we declare it in entity, the same signals or the IO ports can be utilized with other architectures. That is the specialty with VHDL. Now in Verilog, even in the sequential assignment, as I mentioned, there are 2 other assignments called non-blocking assignment and blocking assignment. You can see the symbols used here. For non-blocking assignment, it is this less than equal symbol. For blocking assignment, it is that equal symbol. I will not go into these non-blocking and blocking assignments right now because we are going to discuss it in much larger detail in the theory classes. You will understand it gradually. Now it is too early for you to understand these things. But just remember that there are varieties of assignments. First one is always a concurrent assignment. So we use the keyword assign in Verilog. When it comes to sequential assignment, in Verilog we will have blocking assignment separately and non-blocking assignment separately. Now in VHDL we have these bitwise operators, these logical operators. We directly type not AND, NAND, OR, NOR, XOR and XNOR. Whereas in Verilog, we have this tilde symbol which is for NOT gate, ampersand symbol for AND gate, pipe symbol for OR gate and caret symbol for XOR gate. And when we use the tilde along with the ampersand, it is NAND gate. When we use this again with OR, it is NOR. When we use this tilde with caret, it is XNOR gate. This is bitwise operators. And in Verilog, we have this logical Boolean operators. In Vhdl, there is no specific keyword for that. Whereas in Verilog, this exclamation mark is for negation and double pipe is logical OR and double ampersand is logical AND. Where it is not a bitwise operator, means bit by bit output will not be computed. Again, more about it will be discussed only in the theory classes. Now there are these conditional equations. If A equals 0, then else, and if. There can be statements in between. If A is 0, then what to be executed, else what to be executed. But here in Verilog, that then will not come. If and else, that and if will not come. Because anyhow at the end, begin and end are there in the always. That is corresponding to that end. And in the loop syntax, this will use, Vhdl will use ELS IF. Inside if, there can be else, there can be else if, it can go on. At the end, there can be end if. See, remember, else and space and if is different, and else if is different in Vhdl. This is another style. There can be nested if statements, then it can be else and then if, then else and then if, or else it can be simply else if, else if, else if. Verilog does not follow that multiple style. It will have only else and then if. So you will have to understand this. If there is one more if, then there must be end if inside Vhdl. If you give else if, then there need not be that end if there. That is the specialty with Vhdl. Now in case statement, case D in is and end case, this is the way in which Vhdl uses the case statements. Whereas here, case within parenthesis, we have to give the D in, then we give end case. Just remember, in Verilog, end case and end module are single word. There is no space there. Whereas in Vhdl, when you put end case, there is a space there. Verilog, end module is the last statement which we type in a program, and there is no space there. Remember that. Now for temporary declarations, we are using signals in the concurrent execution and we are using variables in the sequential execution inside the architectures. Whereas in the case of Verilog, for the same signal we can use the term wire because it is a concurrent execution. And for sequential circuits, we are using reg. Reg stands for register. If you visualize a full adder circuit, now XOR gates output, and that is going to be sum, A XOR B XOR C. And then you have AB plus BC plus AC. Now that is carry. In between them there are wires, right? Between the gates there are wires. All those wires are concurrent, right? Concurrent means as soon as input changes, output changes. Whereas in case of a register, in case of a flip-flop or a counter, output will not change until the clock changes. So in Verilog, we use keyword reg for sequential and keyword wire for concurrency. Same thing in Vhdl, signal is for concurrency, variable is for sequentiality. Now in Vhdl, gate level and transistor level primitives are built in. Whereas in Verilog, those gate level and transistor level primitives are not available. Okay, that is how in Vhdl there can be multiple packages which can be utilized. In Verilog, it is not so. Many times we will have to build our own models there in Verilog. Let me continue to discuss some commonly used symbols and common abbreviations. So is there any question till now?
So will we have like built libraries?
Can you raise your voice? I am unable to listen. Speak louder.
So built-in libraries,
Yeah.
do we have it in this?
Do we have?
Sir, do
I
we
still
have
didn't get it
built-in
fully.
libraries?
In Verilog, we have built-in library. That is why we don't specifically say in the program. But in Vhdl, we use a library called IEEE. And in that library, there are multiple packages. We will be using whichever packages are applicable to our program. Okay, that is how the programs can become more compact. Even though the typing work is more in Vhdl, programs can be more compact because whichever package is utilized, that only is there in our program. Whereas in Verilog, there is no such freedom. Whether it is required or not, by default, it will be there during your execution. The reason is VHDL is really very vast. Because it is very vast, it can have multiple libraries, multiple packages. Whenever required, whoever wants it, they can take it. They can use it in the code. Verilog was basically meant for industrial applications or consumer products, so to say. Now, I'll give an example. Let us say we are going to write a program for one mobile phone. We can do it using Verilog itself. Let us say a mobile phone's complete functionality can be modeled using Verilog, because mobile phone is a completely integrated consumer product. There is not much big of a risk there in the case of a mobile phone. Even if there is a risk in the operating system, it can be updated later on. So in Verilog, there need not be multiple choices possible, because if there are multiple choices, it will be difficult to relate them together when there are multiple teams working. So what they do is, now Nokia releases a new model, or Samsung releases a new model. Let us say iPhone releases a new model. They go on working in this way. They keep on releasing by integrating all the applications into one particular product. There it is easy to use Verilog. But let us say ISRO or DRDO is going to develop a satellite or a missile. Now it is not supposed to fail at all, right? Satellite is not supposed to fail at all. Missile is not supposed to fail at all. It is not like our mobile phone, which is a critical product. It is a real-time product. When it is a real-time product, there is a risk of failure. And when the satellite is put into orbit, it has to work for the next 6 to 8 years, or whatever is the scheduled expected lifespan. So in that case, it has to be as compact as possible, because resources are scarce there. Power is scarce, memory is scarce there. So in such cases, it is advisable to use VHDL, so that whatever package is necessary, that can be put into it. Whereas in your mobile phone, you will have gigabytes of memory available. So it does not matter much of saving the resources here. That is the idea. So in Verilog, there is no choice of library as such. We don't specify any library, because library is built in. Whereas in VHDL, we specifically tell a particular library, and we specifically tell which package we are using. That is because VHDL is a very vast programming language. That is the idea. I hope I answered your question. Any more questions? Okay, let me continue. Students, it is very important that you understand all these concepts of concurrency and sequentiality, because electronics engineers are gradually going to understand how an integrated circuit is going to be designed in future and how an embedded system is going to be designed in future. For an embedded system, it is basically a sequential type. So embedded system is driven by a microcontroller or by a microprocessor in future. There it is driven by a clock. But an ALU or a multiplier or an adder is part of the CPU inside, right? Is part of the microcontroller inside. Now a multiplier is a combinational circuit. Adder is a combinational circuit. Whereas a memory is a sequential circuit. Now all our systems comprise of both combinational and sequential. So why do we have concurrency and sequentiality in this way is because of this. Let us say you are going to write a code for a multiplier or an adder, then that is definitely going to be a concurrent logic. There is no clock there. Whenever you use a clock, then that is going to be sequential. That is why I gave an example of Ravana now. That this language is basically concurrent. Whenever you want it, you are going to tell it as sequential by using the keywords process in Vhdl and always in Verilog. You will understand more about it when we deal with the examples. Now one more advice for me, as classes are going on online. Those of you who are having laptop at home, it is better that you install Xilinx software into your laptop and start working with the Xilinx software. If you want us to help you in installing the Xilinx software, you can come over here to the department and our lab instructors will help you in getting the Xilinx installed into your laptop. But it is better that you start practicing on your own. Otherwise, it will be difficult for you to relate to whatever we discuss. Fine, let me discuss the commonly used symbols now. Tilde, as I told you, is for NOT gate. We use this tick and we use this back tick and we use this quote, single quote and double quote. Single quote and double quote, or we also call it as apostrophe. Single quote we call it as apostrophe. Back tick is different and this front tick is different. We use many times for specifying compiler directives in Verilog language. Verilog uses a lot of such symbols. And you have already seen this double quote and single quote. You have seen ampersand, caret, and we sometimes use this cross hash also. For specifying a delay in Verilog, we use this hash. Now, as far as abbreviations are concerned, CPLD stands for Complex Programmable Logic Device. FPGA stands for Field Programmable Gate Array. The generic array logic is GAL. HDL is Hardware Description Language. IEEE is Institute of Electrical and Electronic Engineers, one of the most reputed organization all over the world, where a lot of technical research in the field of circuit branches is published, summarized in IEEE. Students can always log into IEEE-explore.org and you can always find the publications there. You can find some of my publications also there. You can search for my name and you will find my publications which are published in IEEE. Now, what is IP? Intellectual property. What is actually IP? IP basically means, nowadays, as the technology has evolved, nowadays many of the microcontrollers and microprocessors are no more hardware. They remain as software. And the software is encrypted. Soft core. It is called a soft core. It is not hard core. That soft core itself is sold by those companies. For example, I am having a Nokia phone with me. In this Nokia phone, there is a microcontroller inside, and that microcontroller is not designed by Nokia. If you have a Samsung phone or iPhone, that particular microcontroller which is inside the product is not designed by that particular company. That microcontroller is sold by some other company. There is a company called ARM, ARM, Advanced Risk Machine. That is the company which is going to sell quad core or octa core microprocessors to these mobile manufacturing companies. Now there are mobile phones which are powered with a quad core processor. There are mobile phones with octa-core processor, means parallelly 4 cores are going to work. It is as if it is 4 CPUs are working together. That is how the mobile phones are having a faster execution. Now in such a case, there is actually no hardware for that microcontroller. That is called IP, intellectual property. It is a soft core. And the soft core is going to be sold by these companies, that is going to be purchased by the mobile phone manufacturers, and they will program the chip accordingly. But they cannot see the contents of the soft core because it is encrypted. Otherwise, anybody can copy this soft core and they can use it as a processor, right? So that is why it is called as intellectual property. It is a patented property. They have their own copyright. Let us say Intel makes one microprocessor in future. Intel can use it as a hardware inside his products, or Intel can sell it as a soft core to some other vendors. That becomes Intel's intellectual property. That is called IP. Now there is integrated logic analyzer ILA, and there is integrated software environment ISE. You have to remember this. When we start working with the Xilinx software, Xilinx has got the built-in ISE, integrated software environment. It is also called as integrated simulation environment at times, which means we are going to use with FPGA boards. We are primarily going to program FPGAs. Now in the theory class, we are going to discuss more about the differences between ASIC and FPGA, application specific integrated circuit and field programmable gate array. FPGA is a already manufactured chip which we are going to program, whereas ASIC is the chip that is going to be manufactured after we design it. It is as if you cook food at your home, then that is called ASIC. If you buy food from outside, then it is called FPGA. It is like a real life example there. You don't cook your food, you buy the food, you consume it. Same way, you buy the chip and you program it. That is FPGA. Because it is a programmable IC, integrated circuit. Whereas ASIC is you cook the food on your own. ASIC is you design the chip on your own and get it manufactured. That is the basic difference between ASIC and FPGA. Now, there is a company called Xilinx, and we are going to use that software in our lab. There are other companies such as Altera and Actel, which are also the manufacturers of FPGA. Now, in this Xilinx, we have this ISE, integrated software environment. Whenever you write a software program, in the beginning you require one compiler for checking syntax errors. Now in the case of C language, after the compilation, you will have the linking, right? You will have a linker, and that linker will gradually help you in executing the program. Here in the case of HDL, we have a compiler for checking syntax errors. Later on, we do not have any linker because we are getting FPGA programmed. So we have something called simulator. Simulator means we want to check the code before actually connecting it. Before connecting the hardware, we want to check whether the Verilog code is working or not. Verilog code's functionality is happening or not. That is called simulation. So remember this, simulation means there is no hardware, only the computer is going to show you the output. Emulation means you are going to connect the hardware to the computer system, and whatever you have simulated, you are going to download into an FPGA kit, then that is called emulation. So here also we require a compiler, then we require a simulator. Then later on there is one more process called synthesis, where for a given code, the code should be converted into the circuit diagram. And the circuit diagram actually gradually has to be implemented in the FPGA board. Because if that circuit diagram has to be implemented in the FPGA board, there is something called netlist, network list, where it's a connection of all those gates and wires. So in the FPGA, accordingly, all those gates and wires have to be connected. For that, the Verilog code or a VHDL code has to be converted into the hardware counterpart or the circuit diagram. That process is called synthesis. So Xilinx contains compiler, it contains simulator, it contains synthesis tool, and it contains additional software for drawing the waveforms on the screen. It is also called as GUI, graphical user interface. It also contains additional software for downloading the executed output into the FPGA board. That is why it is called as integrated software environment. Let me continue now. Coming back to symbols, this is asterisk, parenthesis, bracket, brace, angle bracket. Then we have backslash, we call it as, sorry, this is forward slash, we call it as solidus also, and we have backslash, then we have pipe, then we have hyphen, then we have asterisk, we call it as at symbol, then we have colon. We use all these symbols both with VHDL and Verilog for different purposes. And coming back to abbreviations, ISP means in-system programming, which means you connect the FPGA to the computer and you can directly program the FPGA connecting the computer. That is called in-system programming. JKFF means Jack Kilby flip-flop. Remember this? Jack Kilby was one of the pioneers who was instrumental in making the first integrated circuit called voltage controlled oscillator. That's why to honor him, in the flip-flop itself, that particular flip-flop is named after Jack Kilby. There is one more abbreviation called JTAG, Joint Test Action Group. This is especially useful when we connect the FPGA kit to the computer and how the FPGA is being sensed by the computer system. See, inside the computer you have Windows. Using Windows we are executing Xilinx. But how will Windows sense the FPGA kit, which is not a standard peripheral board, isn't it? For a computer, the standard peripherals are mouses and keyboards and cameras and all other things. FPGA kit is not a standard interface to a Windows operating system. So we require some other software which will tell Windows that we are going to use one particular kit for our purpose and only we will understand its functionality. For that purpose, one set of engineers developed a separate set of protocols or a separate set of testing methodology. That is this JTAG. You will learn more about it when we start working on hardware experiments. So let me go faster. I don't have to go in detail about all these other abbreviations. LEC is logic equivalence checker. LMG is logic modeling group. LUT means lookup table. We will be talking about lookup table in the theory class in more detail. NGC is native generic compiler. As I told you, we are using ISE, integrated software environment, which will have a built-in compiler. That is called this native generic compiler. OTP means one-time programmable. In general, we will have one-time programmable memories that are available. We are going to discuss more about them in the theory class. Then PACE means pinout and area constraints editor. This is in some way related to this joint test action groups protocol. PAL means programmable array logic and PCI means peripheral component interconnect. I have just listed some of these abbreviations for the purpose of you understanding the FPGA manuals, because in future when you start working with FPGA manuals or with Xilinx software, the software itself uses a lot of abbreviations. Let me continue now. So now after colon, we have this comma. If it is at the top side, we call it as apostrophe also. And we have this ellipsis, we have exclamation or bang, we have underscore, we have period, and we have semicolon. We use it for different purposes. As I told you, the semicolon is a delimiter. And we have one more abbreviation called PLA, programmable logic array. TBW means test bench waveform. When we write a code for any design, later on we need one more code for giving the values for the inputs. That is called test bench. and the test bench will give out the take out the outputs from the design, and that will be passed on to the GUI interface, graphical user interface, by means of which we are going to see the waveforms on the screen. UCF is user constraints file. You are going to learn more about it when we start interfacing the hardware. VHDL, as you already know, VHSIC hardware description language, and VHSIC you already know, very high speed integrated circuit. Lastly, XST is Xilinx synthesis technology. I told you that we have compilation in the beginning, then we have simulation, then we have synthesis, then we have downloading. So before downloading the program into the FPGA, we need synthesis, means the code should be converted to the respective hardware implementation or circuit diagram. That is possible by means of one more technology called Xilinx synthesis technology, which is built in into the Xilinx software. So with this, I am ending the introduction of this. Now let us start about the steps about executing VHDL or Verilog programs. Now go to the start menu and double click on the Xilinx design suite. You can see this here, ISE. ISE means integrated software environment. That's that Xilinx ISE design suite. When you double click on that, it will open this particular software window. Now here you can see there is this file, and you can see at the left side a new project, open example, project browser, copy project, close project. Here new, open, close, save as, print, all these options are there in the pull down menu. Now understand this terminology, project. Inside the Xilinx software, whenever you go, we always initiate a project. Now the project can have multiple programs. Please understand this. There can be multiple programs. All these programs will contain different codes, and combination of multiple programs is going to be a project. So Xilinx will always say first as project. You can click on a new project. Now you may ask, what for is this new and open? These are for files, and the upper one is for project. Which means, just like we use editors, we use MS Word editor for typing our documents. Similarly, we need an editor even in Xilinx for typing our program. Now Xilinx has got a built-in editor where we can type our program, and that program is going to be saved as a file. Okay, so for that file only we have this new file or open file or closed file. That is this new, open, close. That is meant for program files. Whereas project is a collection of many such files, or maybe one file only, it does not matter. But always a project will contain one main program and one test bench program. Both are required. You will have a main module, or where we will specify what the program is supposed to do. And in the test bench program, you will specify the values for the inputs. So any project by default will have at least two files, main file and the test bench file. So when you click on a new project, you will have to give the name now here. You will have to give the name. You can see at the left side here, you can see that ABBBB, they have given a name for the project. You can give any name here, and you can select its location also. We have chosen it in the D drive. If you want to have a description, you can type a description also for your own self. That's all. Let us say in the industry, many engineers work on a big project. Now, whoever created a project, he should specify something about that project so that later on, others also should understand about it. When there are multiple people working, proper documentation is necessary. Or let us say somebody is suddenly sick, then somebody else has to work on that project. At that time, all these descriptions are necessary. However, in our lab programs, we are not going to use all that because our lab programs are not that big as such. So you have to give a name for the project, and you can select a location. You can see here at the top you have that project name. Below that, you have one crazy looking name, XC6SLX9-3TQG144. Actually, this is the particular name of the FPGA chip, below which you will have your particular program. Here you can say decoder 3_8, and this is the particular program or the file which contains the code for decoder 3 to 8. So this is called hierarchy. Hierarchy means at the top you have project, below which you have the FPGA on which the project is going to be implemented, and below which you have the code which is meant to be downloaded into the FPGA. This is the hierarchy. Now I am going to tell you about the name of this FPGA. Why is it like that later on? Until then you wait. And here again below you can see behavioral check syntax and simulate behavioral model. Now that behavioral check syntax itself is the compilation process. In C language we call it as compilation, here they call it as checking syntax. And after the syntax is checked, we are going to execute that program by giving the values to the inputs. That is called simulation. So you have one option here called simulate behavioral model. You are going to understand all these things later on gradually. Now, when you set this project, there are these particulars. You can see this. We have to select a particular FPGA, right? We are using Xilinx FPGA, Spartan family. In Spartan family, we are using the Spartan 6 versions. If Xilinx has got multiple flavors or multiple varieties of FPGA. Out of that, we are going to use Spartan 6. They have got additional series such as Vertex series along with the Spartan series. But we are using Spartan series, and in that Spartan series, we are using version 6. And in Spartan 6, we have one device called XC6LX9. You don't have to worry much about the abbreviation. It is not an abbreviation, it is the Xilinx reference, that's all. Then you have this package, you can see here in the menu. I'll show you here itself. Spartan 6 XC6LX9, then TQG144, thin quad glass 144 pins. This FPGA is going to have 144 pins. In this FPGA, except for the power supply and ground, all other pins are programmable. In the sense, let us say out of 144 pins, let us say about 100 pins are IO ports. Let us say 44 pins are power supply and ground. Because it is a small chip, it will not have a single supply pin, it will not have a single ground pin. Because it is a small chip, it will have multiple supply pins, multiple ground pins. Because supply and ground are having larger current flow. But as the chip is very small, if it is given with a single pin, that single pin will get damaged. So for that purpose, supply and ground will have multiple pins. So let us say this particular chip is having 144 pins, out of which 44 pins are power supply and ground. Now remaining 100 pins, all these pins are programmable. Whichever we want it to be input, whichever we want it to be output, we can select it that way. Okay, that is the beauty of FPGA. And this particular chip which we are using is glass pack. Now, as you already know, integrated circuit is silicon. Now, this silicon can be packed either as a ceramic package or a plastic package or a glass package. Here, we are using a glass package chip, and it is a thin package. It's a quad package. Quad package means below the package, all four sides we will have pins. That's why it is called TQG, thin quad glass. Now in the mobile phones, we will have the integrated circuits which are called as BGA, ball grid array, where the pins are not at the sides. pins are at the bottom as a big matrix. Whereas with the FPGA, in this particular case, we have the pins at the four sides. That's why it is called TQG. And it has got a speed grade of 3. It is not -3, it is speed grade 3. Then you can see the synthesis tool which we are using is XST. Simulator tool which we are using is iSim. There is one more simulator called Model Sim. This can be integrated into Xilinx software also. But as such, Xilinx has got a built-in simulator called iSim. We are going to use that only. Then the preferred language can be either Vhdl or Verilog. You have to choose this here. Depending upon your requirement, you will have to select either Vhdl or Verilog if you are going to write that particular code. Now in this way, you create a project. After creating a project, now you have to click on that file and new, and you have to type the code. Type the code for your given program, and afterwards you should come down here. You have to add this new source. In the pull down menu, when you come to this new source, you are going to give that particular code into the software now. So you can see here, upper one is project name, below it is FPGA name, below there you will have a code, and you can see what are all options are available here. There is an option called BMM file. There is something called chip scope definition and connection file, implementation constraints file, IP core, MEM file, schematic, user document, Verilog module, Verilog test fixture, Vhdl module, Vhdl library, Vhdl package, Vhdl test bench, embedded processor. These many options are available. Now we are not going to work with all these options in our labs. We are especially going to work only with this one and then this one, Vhdl module, Vhdl test bench. So let me annotate once again. Verilog module, Verilog test fixture, Vhdl module, Vhdl test bench. As I told you, the code you have to write in a Verilog module. Then for giving the values to the inputs, you should have a test fixture or a test bench. So there is a separate code for test bench. These two we are going to use. And in the same way, in Vhdl, we have Vhdl module and Vhdl test bench. Basically, these are the four things which we are going to use. But I would advise you that in this semester, you become familiar with the Vhdl and Verilog. Maybe by the end of the semester, if you have to implement a mini project, use this chip scope. Using the FPGA kit, using the chip scope, you can actually interface an FPGA kit directly into the computer. There's a chip scope option available. Of course, we have not kept it in the syllabus because it is too heavy for you to understand it right now. But by the end of the semester or by next semester, those of you who are interested can work on chip scope. Okay. Chip scope is again one more method by means of which directly the FPGA kit is accessed in the computer. Okay. Now there is something called implementation constraints file. I will not discuss this now. Initially in the lab syllabus we have the programming experiments or simulation experiments. Later on in the next cycle we have interfacing experiments. We actually connect some other peripherals to the FPGA kit such as DC motor or stepper motor or a keyboard and a 7-segment display or a waveform generation board. We are going to connect all that. At that time, whichever pin is going to be utilized as the particular input or output is going to be specified by means of this implementation constraints file. I will tell you about it at that time. Regarding IP core, I have already told. Remaining things I will not go into with larger details. Only thing is, I want to tell you about the schematic. Now there are multiple ways of entering our design into the software. One way is write a code using Vhdl or Verilog. Another way is directly enter the schematic diagram if that schematic diagram is ready. which means let us say you have a circuit diagram. For that circuit diagram, if it is connected as a netlist file, you can directly give it to the tool, directly give it to Xilinx, and it can directly synthesize it. That is one method. That is why we have this option of schematic. But this schematic option is possible only for smaller designs, not for larger designs, because it is impossible for us to write circuit diagram for much larger designs. It is easy to write a code now. In fact, now in the industry, in the MATLAB, they connect many blocks for a given system and they simulate the complete block there at a upper level or functional level. It is a block level simulation. Once the block level simulation is successful, there is a code converter from MATLAB to Hdl. That means from MATLAB, it will directly generate Verilog code or Vhdl code for the block diagram which they tested in MATLAB. That Verilog code can be directly synthesized and downloaded into FPGA, and whatever they simulated in MATLAB is now working inside FPGA. All that facility is now available in the industry. That is why all these options are available in the Xilinx software. So after this, you will have to enter the test bench now. Now you have given the code or program, you have to give the test bench now. Let me write a small diagram here. I am writing a bench here. Okay. And I am writing UUT. You can see that UUT here. And now this I will call it as test bench TB. Okay. I have written a bench here now. I have written a bench here. Below the bench, we have this unit under test. UUT means unit under test. This is our design file. For example, let us say you write a code for one full adder. That full adder's code is this now. Now to the full adder, to that A, B and C in, you have to define the values 0, 0, 0 till 1, 1, 1. That is going to be done in the test bench. So through the test bench, you will give the input to the unit under test, and after the execution, that is going to be passed on to the test bench back. Test bench will collect all these output values and that will give it to the simulator. Simulator will display it in the GUI or on the screen. This is the process. So you visualize this diagram always. Below the bench, there is this UUT. We also call it as DUT, design under test or unit under test. So at times, this test bench is also called as top module, because test bench is at the top and UUT is the bottom. So please remember this is important. So after we enter a code for the given design, we should again insert a test bench in the same procedure. Now Vhdl will generate an automatic test bench, and in Vhdl it will have these many clock definitions. But in the beginning, we are going to work with only combinational circuits, so we will not be using clock. So what you have to do is you have to delete all these clock statements at once, because we are not going to use them anyhow. Later on, when we start working with sequential circuits, we can use these statements. But Vhdl by default automatically generates these statements, which we have to delete. But in Verilog, this is not necessary, because Verilog will not give any automatic clock definitions. There we only have to give the clock definitions manually. So after removing this, what you have to do is, here there is a stimulus process. As I told you, process is what? Process is sequentiality. HDL as such is concurrent. Whenever we want to give an input, then we make it as sequential. I'll ask you later on. If you have understood this, I'll ask you later on about why we do that. So, see, this is the stimulation process where begin, then wait for 100 nanoseconds. A is assigned with the value 0, B is assigned with the value 1 and wait for 100 nanoseconds. In this way, you can give multiple statements. You can give 0, 0, 0, 1, 1, 0, 1, 1. All the four values you can specify for A and B. And for each one, you have to give wait for 100 nanoseconds. Now, can anyone tell me why we have this wait for 100 nanoseconds here in the test bench? Can anyone tell me? Have you understood the question? Okay, you might not have understood the question. Don't worry. HDL as such is concurrent, isn't it? But test bench cannot be concurrent. Why? In the test bench, we have to give 0, 0, then we have to give 0, 1, then we have to give 1, 0, then we have to give 1, 1. In between them, there must be a delay. Otherwise, if at all we make it as concurrent, 0, 0, 0, 1, 1, 0, 1, 1, everything will happen together. So please understand, our main code may be concurrent or combinational logic, but our test bench always has to be a sequential execution, because in the test bench we are going to give values to the inputs one after the other only, and it has to be executed also one after the other only. That is why you can see in Vhdl he has used the word process here. Now this is where we are telling to Ravana that from now on it is sequential. Until then it was all concurrent. Until the simulator encounters this word process, until then the whole program is concurrent. Now from now on it will be sequential. Similarly in Verilog, until there is a word called always, previously everything is concurrent. Later on it is going to be sequential. This is important and you will have to understand this. So now you can see we have given at the top we have project name, then we have FPGA chips name, then we have this test bench, below which we have this UUT. Now this is the hierarchy. Earlier you saw the hierarchy where test bench was not included. Now automatically test benches goes on top of the main module. Reason is test bench is having the input values and that is going to give it to the main code. That is why test bench is also called as top module. So remember this hierarchy. At the top project name, below which FPGA chips name, below which test bench name, below which your design name. It has to be in this hierarchy. If this hierarchy is not matched, your program will not run. Now you have these two options, behavioral check syntax for the test bench also, then simulate behavioral model. Once you click on simulate behavioral model, output will be plotted on the screen. You can see this here. Now the output is plotted on the screen. A and B. A is given initially 0, then later on A is given 1, then B is remaining 0. Output Y is given here. Can you tell me which particular logic is this? You are seeing a waveform on the screen, and can you tell me which particular logic is this? Anybody? Anybody? There are 15 students. No one is responding. No, it is not OR gate. It is AND gate. If it is OR gate, output will become high here, right? Y will become high because A is high. Now B has remained low, A has remained high, output has remained low. So this is AND gate. But all the four sequences of input are not given here. In the test bench, all four have to be given here. Anyhow, this is an example, that's why we are showing it to you. So 0, 0, 0, 1, 1, 0, 1, 1, all four have to be there. That is why that delay of 100 nanosecond you can see here. That delay also you can change. It is not necessary that you will have to make it 100 nanosecond only. But as I told you, test bench has to be sequential. Test bench cannot be concurrent. Your main design module which you write for AND gate can be concurrent or has to be concurrent. Test bench cannot be concurrent because we are giving input sequences one after the other. So with this, I am ending today's class. In the next class, let us discuss our first experiment and let us try to see its output also. So till now, if you have any questions, you can ask me. Otherwise, I will stop recording, but the meeting will be on, and you have to write today's observation book. Whatever you learned now, you have to write down. Anyway, I am going to upload the lab manual into the Google Lab class now. Briefly write whatever you learned today. It need not be very much detail. It can be within one page also. Briefly write it and then post it into our lab class. My colleague Richard has already prepared an assignment there in the Google class. There you can upload. So any questions? If there are no questions, I will be stopping sharing the screen and I will be pausing the recording. So I hope there are no questions. So let me stop, but the meeting will be on.